Welcome back to Agent-Based Modeling for Psychologists. This is tutorial 3, building off tutorial 1 and 2. I imagine by this point, if you're watching 3, it's because you've watched 1 and 2. In the previous 2 tutorials, we've built this quite simple little model, which you can get the code for by going back to the comments below in either one of the 2 tutorials. But we've built a model where we have our agents engaging with the world, doing a semi-random walk. We have these obstacles that we've called rocks. So we have peeps, we have these agents called peeps, and we have rocks, these obstacles, and they can walk around the world detecting, perceiving those rocks, and then modifying, for example, the degree, their sensitivity, their visual range. So right now their visual range is quite close. Or we can expand their visual range so that they're much more avoidant. And it's from this model today that we will be building on the capacity to detect objects in the environment, but this time seek them out. So how they can orient kind of in a more calibrated sense towards these objects, and how we can build in variables for memory. So really simple things, just like remembering how many items of food they've eaten and so on. So that's where we're going to start today. So if we look at our code, let's just review what we've established. We've got 2 different kinds of breeds. We've got rocks and peeps. Peeps are our agent. Rocks are obstacles. We have our setup code where we clear everything. We create our peeps, we create our rocks, and we reset the ticks. So far, we populate the world with 10 peeps at random locations, and they're all the same size but different colors. We randomly populate the world with 10 rocks. They all look the same and are stationary. And then when we consider our go commands, the peeps move, the peeps detect rocks, and then they also check whether their trails are down, and this code develops that. So when we think about expanding the model to do what we need to do, we should probably sit down and write out everything we want to achieve. We're not going to do that. I'm going to build it up in a stepwise process that is pedagogically useful, but not necessarily the best for like building a sophisticated model. By the end of today, we're going to have a kind of food, a resource in the environment. We're going to have our agents detect that food, consume that food, but most importantly, if they're eating food, there's no point in eating food unless that matters in the model to the agents for some reason. So we're also going to implement a system of energy expenditure and energy consumption, and we're going to have to address issues associated with death, potentially, what happens when they reach 0 energy, and maintaining an equilibrium between our resources, our food, and our agents, because if they're eaten, they disappear, then what? There are multiple solutions for that. We're going to go through one of them, but I'm going to build this up in a stepwise process that best demonstrates how to do the coding. If I were to do this with the intention of building a model for evolutionary type dynamics, I would probably do this in a different order. So just keep that in mind. So first things first, it seems like we need a resource. We're going to need a new kind of turtle that's neither an obstacle, a rock, nor our focal agent, our focal turtle, which is our peeps. We're going to need something called a resource. So I'm just going to call this foods and food. Remember the plural form and then the singular. We're going to declare that there's a third breed in this world. And these breeds are foods and food. Declare that foods exist. Now, the reason I'm not just calling it a resource is because in another kind of model, we might have different kinds of resources. Food resources, water resources, or whatever. That starts to get complicated, and these models are all about simplification and abstraction. So we could just have it as resources, but there might be different reasons for it. I'm just going to call it foods because sometimes the natural language is easier to manage. We're also going to need to decide how prevalent the food is. So we've got our commands here to make the peeps and make the rocks. Let's create a procedure called make the foods. This creates the food. We can probably just borrow this. So we'll take either one of these commands. They look quite straightforward. Make the foods. And now we're going to do a little something with make foods, with the creating of the foods. We want to establish a kind of ratio of foods. So for the moment, we'll leave that at 10. Let's build some basic assumptions. We probably want our foods to show up at random locations in the world. We'll set their size to be small, but we will set their color to be something distinct from the rocks and from the turtles. So make all the food green. Now, I'm speaking from experience here that we're going to need to think about the ratio of foods to turtles. So we're going to create a couple of global variables that allow us to set these things at the setup phase when we parameterize this. So we're going to go back to our interface and we're going to introduce some new widgets, and we're going to introduce some sliders. Okay, so let's create 3 to begin with. One is peep population, and we can keep that between one peep and 100 peeps. We could make that any number we want. And the increment, because we're dealing with a discrete agent, we want that to be whole numbers. So let's keep our peep population to be 50, or rather between 0 and 100, we'll let that default value. And let's create a food ratio. Food ratio. And the minimum will be 1. The maximum will be, let's say, 3. So there might be 3 times as much food as there is peeps. And we're probably going to want our increment to not be whole values between 0, 1, 2, and 3, but probably tenths, so 0.1. And we're going to do this because we're going to introduce our first mathematical procedures here. We're not going to vary the number of rocks because I don't think we need to. I don't think that's going to be revealing in any interesting way. And let's just, for the sake of convenience, set our ratio to 1. So we have these 2 global variables that we've established here in the interface. Now, I mentioned in the previous tutorial that introducing global variables in the interface is useful, but if you're just looking at the code, you might be forgiven for not realizing they're in the model because they're in the interface. If we're not declaring our variables in the interface, we need to establish them here in our code before our setup procedures, usually done at the top where we're establishing our breeds. Now, globals are variables that are accessible from any part of the model. So vision is a global variable. So when I call vision down here, it's being called from the interface, essentially. Not all global variables will be established in the interface because they might change within the context of the model. So we're not able to double declare a variable. So if I write global's vision here, it's going to tell us there is already a global variable called vision. Peep population and, what did I say, food ratio. Food ratio. Now, these are all going to throw up errors, and they're going to throw up errors in the order they occur. So if I cancel out vision, it's going to just move to the next one. And so I'm going to include these here, and I'm going to annotate them and say global declared in interface. And this is just going to let anyone who's reviewing my code not be confused as to what the difference is between a global I might declare here at another time, like, I don't know, death age at which a peep dies, for example, and globals I've declared in the interface. So I'm going to cancel them out, or they will throw an error, but they are functionally the same things. So let's modify the code we've got. We've now got a global variable called peep population, just like vision. Create peeps. peep population. Create as many turtles as the interface dictates. So, peep population, if it's 50, we now have 50 turtles running around. And because it's called its setup, if we change it here, it's not going to make a difference. But if we change it before we call setup or afterwards, it will make a difference. We've got different sizes going on here. So what's happening? And so we have these little ones. That's a simple oversight because I've copied the make the foods. I copied the make the peeps, and I've just created foods, and we've just kept all the code there. So this was actually an oversight on my part. We're learning how to identify and debug errors. Now you can see it's working just fine. We had some orphans code there that shouldn't have existed. So we can now, in our setup, set our global variable in advance for that. So now we want to actually engage with our make the foods. Let's keep this off the table for the moment. We all have them one size. We want their set shape. Let's make it a circle as well. So now if we keep this open, you'll see, let's make them even smaller. So they're 0.5. We can make our shapes, our sizes, decimals. So now we have a somewhat busy scene with small foods, larger rocks, and even larger agents. But now, as I said, we're going to do our first little bit of maths. We want the number of foods we create in the environment to be relative to the number of agents in the environment, for the reasons that will become apparent later. So instead of saying create foods or create with a standardized number, we can base this number on a mathematical operation. We already have the variable peep population, so we know what that is going to be. And what we're simply going to do is type our asterisk in here and make this multiplied by the food ratio. So we can have, when we have mathematical operations, it's often neat to put them inside these parentheses so that we know that they're distinct. We click check. Nothing is throwing up an error here. So what's happening is it's creating foods, which is now this kind of value, which is not obvious to us, but can be dictated in instances. So when we have 30 food, we now should have 30. When we have 30 peeps, we should have 30 food. So let's do this stuff we learned in tutorial 1. Count peeps, 30. Count foods, 30. If we make our food ratio 1.5, we should have, and let's hit setup, we should have 45. So we have 30 peeps and we have 45 foods. And if we make it 0.5 or some other value, 30 peeps, 21 foods. So this will become apparent later, but it's just a nice way of showing that we can have these global variables that can be mathematically operated upon. Which if we visit our Netlogo dictionary and we click maths, we can see that we have all of the standard kinds of things. We have plus, multiply, minus, divide, raise to the power of, and then these kind of logical type operators, which are less than, more than, not equal to or less than, equal to or more than. And then we have some other more complex mathematical terms like cosine, exponentials, square roots, and sine. But for the moment, we're going to deal with the very simple standard mathematical operators. So we've now got an environment that has rocks, agents, and peeps. This is looking pretty busy to me. They aren't actually moving and identifying food at the moment yet, but it's looking pretty busy, especially if we're running it. So let's modify our world for the first time. Let's go up to our settings. We've seen this in tutorial 1 and tutorial 2. Let's make our world larger. Now, without changing the number of agents in the world and the number of rocks, the effect of making the world larger will just basically spread everything out. You may have good reasons to have a world of a specific size, and that there will be implications for the size of the world. But let's make the world a little bit bigger, 25 wide, 25 tall, and it's now 51 by 51 because we have our 0, x, y in the middle. Now what's going to happen is our world is going to get immediately larger on our screen. Okay, much too large to kind of fit in. And I am zoomed in. It probably will fit in on your screen, but I'm zoomed in. What we can now change is the patch size. Let's change the patch size from 12 to 8. And it's about the same size as before. And if we hit setup, we can see that everything breathes a little bit more. There's more space between everything. Okay. And our implications for how big or small vision is are being played out also more clearly. So we've now manipulated our world and just made it a little bit bigger. And this is mostly for aesthetic reasons at the moment, but it will have implications for, say, visual range. And hopefully that's obvious. So we've got our foods, we've got our world. Now let's create code for identifying how. Now let's make our code to identify food and then seek it out and engage with it in somehow. So everything is set up just fine, okay? And now if we want to make things a little bit tidier, we can also go to these little arrows that appear when we go to the margins. We can just click down and we can make these codes disappear. These procedures disappear. We can just make things a little bit tidier as we're proceeding through this. So let's visit our go commands. Our agents move, our agents detect rocks and turn away, and they check their trail. Well, something that's important in Netlogo is scheduling, the order in which things happen. Our trail check is the least important, so let's move that right down to the very bottom, just before tick, because we're probably not going to be using that much more. It's functional code. The question is, when do we want our agents to detect food? And assuming they're going to orient towards it in some meaningful way, how do we want them to move as a result? Our code already stipulates that when we ask them to move, they move forward and they move in a little and then they have a little random wiggle. And then they detect rocks. If they detect a rock after moving and doing a little random wiggle, they'll just turn crudely around in the opposite direction. And then they'll move away from it on the next step because the cycle will repeat. So the question is, when do we want them to detect food? If we put detect food after detect rocks, they're going to step, wiggle, and then maybe turn away. And then we could have them detect food. But is that the correct order of operations we want them to engage in? This is going to be a question for you to answer yourself, depending on what you want. Now, we could just build essentially a detect rocks function, which is a detect food function that happens only after they turn around. And that would essentially work, but work crudely. We could have a conditional set up in our move the peeps, but we will use the kind of cruder version to begin with. So let's, to detect food, and let's end it. Let's get rid of that. We can ask peeps, we've done this before, if any foods in cone, then we can get them to orient towards it. Now, here we come to a question about modeling. We've already established they have a visual radius, or a visual cone rather, that is a given distance and a given pie slice, subset of that circle. Should we have a different visual system for detecting food or no? Well, we could, but I don't see a justifiable reason for it. So I'm going to suggest that whatever they're doing here is going to be visual detection. So we're probably going to consolidate our detect rocks and our detect food into a visual detection procedure. But for the moment, we can do it distinctly. If any foods in cone radius, well, here's our problem. We don't know where they are in the radius. How do we get them to orient towards it? they're detecting something here, but they might not be pointed directly at it. So if they step forward, they might not be able to find it. So let's visit our dictionary. And then let's have a look at what we can see in our turtle related. So there are a bunch of things here that might help us orient towards patch add heading to distance, where we're looking for a turtle, not a patch. So maybe that's not quite right. We've already looked at is agent or inspect. What we actually want is, oh, we see a word that's towards. Maybe that's useful. So let's click on that. Towards agent reports the heading from this agent to a given agent. So we could say set heading towards turtle 1. This looks pretty useful, but it does require us to have identified not just that food exists in the radius, but to identify the specific ID of the food. So this is maybe a little bit complicated, though this would work. Let's see also face. Face agent. This cuts out the middleman, the middle step of kind of set heading towards a named agent, and face just says set heading towards it. We don't need to know what that number is. We can just go, hey, face the agent, face the food. So face seems like the tool we want. So if any foods in cone vision 90, we can just say face foods. Okay. Now, this isn't going to work. This intuitively might work. Oh, that should be foods. This might intuitively work, but it's reporting an error. We've used the plural form, face foods. So what it's trying to do is face all of the foods at the same moment. And that's not going to work, okay? It's going to throw up an error. It's just saying, instead of getting a turtle or a patch, an individual, it's getting an agent set instead. So let's make this singular, face food, okay? Now it's giving us an error. It's saying unexpected closing bracket. And the reason for this is it's expecting another piece of information. So when we use the singular, for a breed, it wants us to identify which food it is. So we want to face food with ID 2. That's going to work now. But we don't know. The point is we want this automated. We don't know what food is closest to them. So we're going to have to come up with a new way of identifying a strategy for our peeps to, once they detect a food in their visual range, how to face that food without us having to worry about identifying exactly the position or the identity of that food. So let's return to our dictionary. Now we can skim through these link-related agent set. Agent set's probably what we're interested in because we have a potential number of foods they should be orienting towards. We have an agent set of food, but we don't want all of them, okay? We want something like a member. And what we see here is a command we've used before in passing is one of. We want them to face one of the foods. And this is quite simple. One of any number of agents. So from an agent set, it reports a random agent. If the agent set is empty, it shows nobody and will throw up an error. So we could simply say face one of foods. And we need this to be plural again because we need this to be an agent set. Face one of foods. If we check it, it'll work. And if we run it, what we want to see is when the trails are down, our agents pursuing foods in their visual radius. But that's not going to happen. And let's see if we can identify why. Let's make it slower. And we'll make the vision a little clearer. You can see here that it probably detected it, but didn't move towards it. Okay, down here the same. Lots of close encounters, but none of them are actually pursuing the food that's immediately in front of them. And the reason for that is it's saying face one of the random member of this agent set, face one of foods. So they identify a food, and then they face any random food in the world. This turtle might see this food, but then it might face this particular food. So we've just added more random to the system. What we want is to identify foods in the visual cone. So there are a couple of ways to do this. A nice simple way of doing this, not perfect, is to, let's go back to our agent set and we skim through this And we have these commands called with. So we might want to identify agents with a certain quality. Face the blue food, face the green food. And we have with max and with min. So a simple way to do this might be to have our agents face food with min distance. So distance is also a command in Netlogo. So what we're saying is like, once you detect a food, face the food that's closest to you. Okay. So we'll implement that, but we're not going to stick with it. Face one of foods with min. And we know, just because I explained it to you, that there's a feature called distance, and distance reports the distance from the agent that calls the command to a given turtle or patch. And the way we declare this is distance to myself. Okay, so we can have this with min distance to self or myself. And what we're saying here is if any foods in cone vision 90 face one of the foods with min distance, distance myself. And now, instead of facing a random food somewhere else, when they detect food in their environment, they should then pursue it. And you can see that in many cases, they're walking straight through food items. Our trails are showing us that they are in fact walking towards it. Now, the issue with this code is that an agent might detect food in front of them in their visual code, but the closest food might actually be behind them. So they're actually pursuing food that they haven't detected, but it's being called here. It's being called here by the command. Now, maybe we don't care about that. Maybe we do, but this is a useful way of looking at this. Now, another way to do this would just be face one of foods in cone vision 90. Okay, so we could just repeat that same line of code. And now instead of looking for the closest food around them, which is in elegant, although it's a useful little strategy we've just demonstrated, now they're specifically looking for that piece of food in their visual radius. Okay, and you can see here that functionally we're getting the same thing, and the agents are now moving through their food and seeking it out. As we go forward, we might end up creating a new way to identify this to make our code more efficient. But for the moment, I'm going to leave this as is because it's basically very clear to read and understand what's happening. But I do think we should consolidate our code. Now, we might wish to consolidate these two into some kind of procedure that's like detect environment. And there would be good reasons to do that because now if an agent, in the order it happens, an agent's going to move and wiggle, and then if they detect a rock, face the opposite direction, and then they're going to detect food. But is this like the sensible way? Should we make it another way? If we had it this, where they move and wiggle, and then detect food, and then orient towards it, and now it's going to logically be the case that if there's also a rock near the food, they're going to turn in the opposite direction. So if we have this, and I'll cancel this out because that doesn't do anything. If we have this, what we're going to see is that food near rocks is never approached. Let's make this vision a little larger so the example will be clear. Turn the speed up. And you can see here that food near rocks will never be approached, okay? Because they move and they wiggle, then they orient towards food that they detect, but if it's near a rock, they run away. Now, if we move detect food to after detect rocks, we're probably going to see a similar problem, but to a slightly lesser extent. I'm not changing any of the parameters, so let's hit setup and go. Okay, and they're getting maybe a little bit closer to some of these foods that are like possibly within the range, but the similar thing is happening. So the question will be, how do we want to schedule these events? Do we want them to be afraid of rocks at the expense of food, or do we want them to overcome their fear of rocks so that they can pursue food? That's going to be a question for you and your model. If we had a detect environment procedure, we might make it so that if they detect a food, they approach it and ignore rocks, or some other set of concerns. In subsequent tutorials, we're going to let vision evolve. So we're going to let them be more scared of rocks than they are desirous of food, but we are going to let vision evolve so that their fear, okay, which is going to be like a proxy of their vision, is going to kind of adaptively change over time. So a more elegant solution would be to have a detect environment. But now for the moment, we're going to keep it so they move and then wiggle. If they see a rock, they turn in the opposite direction. And once they've satisfied their fear drive to turn around and move away from a rock, they then identify if they can see any food in their environment, and then they'll subsequently step towards it and wiggle. But as we can see from our model, we do in fact have our agents interacting with food, or rather identifying food and then moving towards it. But they're not doing anything once they eat food, or they're not doing anything once they get there. So how do we make them eat the food? So from here, we can make some changes here. We could put an eat food procedure in the detect food, but this starts to get weird and messy and nested. Or we could have an eat food procedure here, that if food is detected in one's immediate environment, they eat it here. But we're starting to have very complex, we're starting to have some messy code here that I think we can consolidate. And we do want an eat food command, but we're going to leave that for a moment. And I'm going to demonstrate another principle. Within our go commands, we ask them to move, detect, and detect. And each time we're asking peeps, asking peeps, and asking peeps. Let's consolidate that. Let's just ask peeps once up here to do everything that we want them to do. And then we can get rid of all of this. So then we can get rid of all of this. Now we have ask peeps and then ask peeps, ask peeps. Now we've got it 4 times, but we should just be able to get rid of all of this and really consolidate this code to be fewer lines, and fewer lines is usually better. And so here we can just ask peeps to move forward and wiggle, ask peeps to detect rocks, if any rocks, and to detect any food. And everything functions exactly as we had before. And so now we can have our eat food procedure without having to call upon our ask turtles or ask peeps function again. So let's build to eat food. Remember, we always start with 2 and we end with n. And we want them to, having detected if any foods are in radius, they're moving towards it, or they're ultimately moving towards it. But we now have to make the assumption, can they reach with their hands? How close do they have to be? Well, I think a simple solution is that they have to be exactly on the food. They have to be standing over the food. They can't be distance 5 away from it. They can't be distance vision away from it. They can see further than they reach, and that's pretty true in biology. So let's have them see further than they reach, and they can reach only where they're actually standing. So let's go back to our dictionary, and we skim through these things, and we can see that we've faced. We can jump. That's not useful to us right now. And we see here that there's patch here. Well, that's potentially useful. Patch here reports the patch under the turtle, but we're not interested in patches at the moment. What we can actually see is that in addition to patch here, there is a turtle here. Reports an agent set containing all the turtles on the caller's patch. Okay, so if there's a turtle standing here and it's ask turtle 0, show count turtles here. So how many turtles are right where that turtle is standing? So in our eat foods, we can go if any foods here, because remember, this allows us to do breeds here, and we want to know if there's foods here, not rocks here. Okay, if any, and this is essentially going to be reporting if it's true. So we could also have if any foods here equals true is going to be exactly the same as if any foods here. And now we could have something simple. We'll just use a print command. I am standing on food. And let's run and check. We'll clear our command center. And we can see that when they reach food, they are in fact triggering the command to declare that they're at food. So what do we want to do now that they've found it? Well, they're going to eat it. So Operationally, we need to consider what it means to eat. I think it means, at a minimum, that that food is going to die, or at least disappear. And here we can have a nested command where one turtle calls upon another turtle to do something. We're specifically asking, we want to ask if any food's here. So if any food's here equals true, we can go ask one of foods here to die. They're going to disappear. Okay. Or even we could have ask foods here, which would be all of the foods. But just in case there happens to be two on one spot, we're just going to stick with one of, a command we're already familiar with. We've used it before. If any foods here, ask one of foods here to die. Okay. Now, this should mean that eventually the 30 foods we have here, if we let this run, we're down to 5. We can see that our food count is dying. Those turtles are now dying. Those food turtles are dying, which is great. They're being removed from the system. Our peeps are eating the foods. Okay. So the question then is, how many? What happens after that? The peeps are eating the foods, which is really great. But let's ask ourselves the question, why are they eating the foods? And let's make a note for ourselves. Foods disappear but don't reappear. How to fix this? We'll come back to that. So in a model where peeps are eating foods, we have to assume they're eating foods for a reason. In this case, we're going to give them an energy variable. They're moving around and they're gaining energy when they eat food. Which brings us to a nice set of learning opportunities. So when we visit our dictionary, we know that we have variables, built-in variables, total variables. We have breed, color, heading, hidden, label, size, shape, and so on. I mentioned in the previous tutorial that we can add variables to our turtles, which is exactly what we're going to do. We're going to add an energy variable. We have a breed and they can own a variable, and I'm just going to tell you what this is. You can look it up in the dictionary, but we're concerned with our peeps and we want them to own something, and we're going to give them a variable called energy. Now, unlike a global variable, which is accessible at any point in the system, the energy variable belongs only to peeps. Foods don't have an energy, rocks don't have an energy, just peeps. So if we check that, set it up, and right-click on a peep, we can now see, and I can't make this bigger, I'm afraid, that there is a new variable down here called energy, and it's currently defaulted to 0. So they have energy. Great. When they eat food, let's let them gain energy. Now, we don't need an exact, in this instance, an exact like transfer of properties from the food to the turtle. We haven't given the food an energy variable. So we're just going to assume, for example, that all food is worth 10 energy. So if any food's here, ask one of the foods here to die. Now, for the first time, we're going to build some nested commands within the procedure. We're going to say to our turtles, we want them to increase their energy. So we're going to, for an existing variable, we always say set. Which you can see here we've done for set size. We're going to say set energy. And we're going to say set energy 10. Okay, now we're going to, I'm just going to turn the ratio up so that this is going to be more likely to happen. Let's identify a turtle. We can see this one here has energy as 0. Let's circle it so we can see it more clearly. And now we're just going to look to see if eventually our turtle can find food. Oh, and it's happened very quickly. We can see that our brown turtle has got 10 energy. But it could be the case that this turtle is going to keep finding multiple instances of food. In fact, let's demonstrate that. when they find energy, let's get them to print, I ate food. Let's check. And we can see that lots of them are eating. Okay? Which is good to know. Now, presumably, some of these turtles will have eaten more food than others. So let's ask our turtles, ask peeps, print energy. Now I'm just asking them to all report how much energy they have, and then we can see that they all report either 0 or 10. Now some of them must have eaten more than one piece of food, so we want them to have 20 or 30 or 40 energy. What's actually happening is every time they find food and ask it to die, they just set their energy to 10 no matter what the previous state was. So we can do a little bit more arithmetic, and we can just say set energy, energy plus 10. Okay, this is going to take their existing score of energy and then add 10 to it. So if it's the first piece, they'll have energy 0, 0 plus 10, 10. If it's the second piece, it's going to be 10 plus 10, 20, and so on. Now let's let the model run. It's probably long enough. And we can see some have eaten 2, some have eaten 3, and one has even eaten 5. That's a very successful turtle. So now we've got them to incorporate an updating variable that's unique to each particular turtle. And as you can see here, just here, that some have more than others, and that's going to be unique. This is why it's not a global variable, it's an agent variable. We probably don't need them to report that they're eating food all the time, but we'll leave it there, perhaps because we'll use it later. But now we can ask ourselves, well, once they have this energy, what's the point in having energy? Well, let's add another variable that doesn't increase only under the specific condition of finding food. Let's make it important for the agents to find food. Okay, let's make it so that they have energy, and every time they step, they lose energy. Okay, so we want to probably tie that to the fact that when they step, there's a metabolic cost. There's an energy cost to moving. So we know how to do this. Set energy and energy minus 1. For each step the peep takes, they lose 1 energy. So now in Move the Peeps, they step, they lose 1 little bit of energy, and then they do a little wiggle, they detect rocks, they detect food, and then if there's any food around them, they eat the food. So let's run the model again. We know how to inspect our agents. Let's ask our agent, ask peeps, print energy. Well, we've had 2,520 ticks. Some of them, well, they're all deep into negative energy, but all slightly different because some of them manage to eat more food than others. What happens when they get 0 energy? Well, we should ask them to die. Okay, so eating food, let's get them to check death. Always good to have a check death command in here. To check death, I'll close it out with an end. And this is very simple because we've already asked our peeps to do this. We'll just say, and let's check our dictionary. And let's go to our maths. We saw this before, that they have less than or less than and equal to. So let's just make it so that if energy is equal to or less than 0, those peeps die. So now if we have this world full of peeps, they take a bunch of steps and they die very quickly. They all die, in fact, on step 1. Where at tick number 0, we hit go. They're all dead immediately, except for one or two. And I guess that's because they happen to spawn on top of a piece of food. 3, 4, 5, 6, 7, 8, 9, 10. Our brown one is dead. And we can see here that this one is surviving. but ultimately dies and runs out of food. So our model, which seems sensible to avoid rocks, detect food, all of our agents are going to die very quickly unless they get lucky and spawn on top of food immediately. So that's a problem. We need our agents to initialize with some amount of energy. So let's consider our setup commands. Let's consider the place where we gave them random locations, a specific size, and in some cases a specific color. Let's let them initialize with a specific amount of energy. Set energy, let's say 100. Now this should mean that all of them get essentially 100 free steps before they die, assuming they don't find food in the process. Let's see what happens. Good, good, good. They're moving. They're looking for food. 50 ticks. Everything should be fine. Once we get close to 100 ticks, we might start seeing our first deaths. 90, 100. And then they all quickly die afterwards. So what's happening is 100's not enough. Either 100's not enough to start with, or the amount of energy they're receiving is not enough, or they're not finding the food efficiently enough, or, as might be the case, count foods 24 instead of the 30 we would expect. They're eating food, but the food that remains in the model is food that's kind of inaccessible to them because it's too close to a rock. So let's go back to our note here. Food disappears, but doesn't reappear. How should we fix this? There are lots of different ways to fix this. We could make it so food randomly appears every single tick according to a fixed probability. We could have it so that our agents, if they eat food, 5 steps later they poop out a seed and then a food appears there or something like that. A really simple, elegant solution is basically to say if a food is eaten, then a new one just randomly pops up somewhere else in the map. And the reason we might want to do that is because we've already established that we want a fixed food ratio. We always want 3 pieces of food for every 1 turtle, for example. So down here, when we look at our eat food, we can start making other commands as well. So if there's any food here, we can ask one of the foods here to die. Then we go back to talking to the turtle. That turtle then says, increase my energy by 10. We could then maybe get the turtle to create a new food somewhere else. Like it just randomly asks a patch to spawn it for us. Or we could just do something much more simple. Instead of having our foods die, we just need them to disappear from the place where they're being eaten, right? We don't need them to disappear and then reappear. That's multiple steps. So we could just ask our foods to randomly relocate somewhere else. And we've used this before. Set xy, random xcore, random ycore. So now instead of asking the food to die, we ask if any foods are here. We ask one of those foods to teleport somewhere else really quickly, which is a simulation of death. Then our turtle increases their energy, and then that food is now available in the environment, and the ratio of food availability remains constant across the model. So now if we run this, we can still see that the agent's are dying. The calibration is off, but if we ask how many foods are in here, we can see that there are 60 foods, which is 2 times 30, so that number is consistent. How do we make it so our agents live longer and survive longer? Well, let's make our food more valuable. I don't know, now they get 50 energy from each food. But hey, why would we want to keep editing our code? Let's create a widget, a slider, and create a value called food value. The minimum will be, let's say, 10. The maximum will be 100. The increments, let's make them 5. So now our food value, when an agent eats it, is, let's say, 50. We've got this global variable declared here. And what we want is food value. So now it's going to be energy plus the food value. Let's see if 50 lets our agents survive longer. Okay, we've just passed 100 ticks. We've just passed 200 ticks. We can see the model speeding up because there's fewer agents in there. But you can see that they're now surviving longer. Let's make the food value 100. That's 100 ticks. Speeding up a little bit. The model will get faster the less operations it's running. So as agents die, the model moves quicker. We're just about to crack 300 ticks. There it is. 400, 500, 600. So we can see that it's working. As we make the food value higher, they're able to step longer and search longer. Now, this is one of the really nice things that emerge out of agent-based modeling is we can see what's happening. We have, I think we have 1 peep, count peeps. We have 5 peeps. Ask peeps, set color red. Ask peeps, set size 5. Here are our 5 peeps. We can see they're avoiding rocks, but all the food, because it's randomly spawning to random locations, is spawning near the rocks and isn't being able to be eaten. This presents us with an interesting kind of problem. How can we get our agents to kind of be more adaptive in seeking out food and avoiding rocks? What's the trade-off that we want to make here? So that's where we're going to stop on today's tutorial. What we've done today that is different from our previous tutorials is we've given our peeps, specifically our peeps, their own unique variable called energy. We've discussed global variables, and though we haven't created a global variable in the code, we understand that our interface variables are global variables. We've learnt that we need to often manipulate the variables of our turtles when we set them up, so we give our agents a starting amount of energy. We've gotten our agents to detect food in much the same way as they detected rocks, but instead of turning away, we identified how they can face the kinds of turtles, the foods that they identify in their radius. And then if they identify them, or as might be the case here, if they just perchance happen to be standing on some food, they can then ask that food to either die, or in our case, just move to a random location to simulate death, and this keeps our food ratio constant. And we can update our energy value gains by food, and we've also looked at the logic of why these agents might have energy in the first place and why they might be seeking it out. And it's so that it's because when they move, they expend energy. So, like and subscribe, there will be more tutorials coming up. In subsequent tutorials, we're going to actually look at allowing our agents to kind of engage in evolution. They're going to mate and they're going to reproduce. And we're going to allow our vision variable to evolve, to look further or look closer. And we're going to try and identify if there's an emergent property in our agent-based model that is adaptive for the agents over generations.